Hey everybody, it's Mr. Carr again. Today we're going to be looking at solving some equations here. Specifically, we're going to be looking at solving exponential equations. We're going to use what's called the one-to-one property to help with that. Okay, so we're also going to be able to use some other, like our logarithms, to help us with that as well. But the main goal here is to solve. So, for example, we're going to look at solving these exponential equations here. So 4 raised to the x plus 2 power equals 16 raised to the x minus 3 power. So what makes this easier is if I can turn everything into the same base number. So instead of dealing with 4 versus 16, maybe I can change them into the same thing. Now, thankfully, 16 is the same as 4 squared. So I can rewrite these expressions using, or at least the right side of the equation, as 4 squared instead of 16. If I also wanted to, I could bring them all down to base 2, but that's going to be a little bit more work because 4 is equal to 2 squared and 16 is equal to 2 to the fourth. That creates a little bit extra work, so I'm just going to stick with this definition and use it here. So I got 4 raised to the x plus 2 power is equal to 4 squared raised to the x minus 3 power. Now, the idea here is that if I take the 2, this is going to distribute because I am raising a power to a power. So I have 4x plus 2, and then 4 to the 2x minus 6. So another thing I can do with this is if we look at it, I can apply the same logarithm rules to both sides of the equation, just like any other equation. So if I do the same thing to one side, I can do the same thing, do something to one side, I can do the same thing to the other. So if I evaluate log base 4 to both sides, I will actually cancel those out. So I'm left with x plus 2 equals 2x minus 6. Okay, so that's what I'm working with there. This will be minus x minus x. I'm going to add 6 over here. So I'm left with 8 equal to x. When solving these problems out, you always want to do a quick double check. Does that work in the original problem? And it should, because I've got 8 plus 2 is going to give me 10. 8 minus 3 is 5. So 4 to the 10th power should equal to 16 to the 5th power. Okay. So here we have another one. So we'll solve this exponential equation here. Same thing. I want to turn this into the same base number. Thankfully, 3 and 81 do have I can do 81 in terms of base 3. So that's the same as taking 1 over 3 to the 4th power. Okay, so when I do this now, I could, so what I'm allowed to do is I'm going to take this exponent here, this 4, and multiply it to that power. Because this is the same as if I took 1/3 to the 4th as well. And I'm raising that to the 2/3 power. So because of that, I'm going to have 1/3 to the n power is equal to 1/3 to the 4 times 2/3 power is going to give me 8/3. Okay, so now again, I can evaluate the log base 1/3 to both sides. So that's gone, that's gone. So I'm just left with n equals 8/3. Oh, okay, I wrote 8, so let's do that a little bit better. Okay, so n equals 8/3 in this case. All right. So logarithmic equations, we kind of done some of these here. So the idea is that we're going to use our properties to undo certain steps here. And we're using the inverse idea. So first thing when I look at this one, we're round to the nearest thousandth. First thing I want to do is I want to turn the 2 up here. So this will be natural log of x squared is equal to 18. So remember what natural log is log base e. So I can rewrite this logarithm into kind of the exponential form. What I mean by that is this is base e is what we're officially saying here. E raised to the 18th power is going to equal to the x squared. So from there, we can just square root both sides. So if I do that, I'm going to take the plus or minus version of that because I am solving using square roots here. So I'm going to take the square root of e to the 18th power. And that comes out to a plus or minus 8,103.0, it says nearest thousandth, so 0.84 for my final answer there. And I just want to one last quick double check on here. Even though I solved it through this method, I did do a square property here, I got to be a little bit careful because when I look at the original problem, the negative is not going to work here. Remember, we cannot take logs or natural logs of negative values. That doesn't work out. So because of that, I'm actually just going to get rid of the plus sign or the plus or minus sign. And my final answer is 8,103.084. Okay. So now I do want to mention that there is another way I could solve this too before I move on, actually. So 2 times the natural log of x equals 18. We can actually divide both sides by 2 to start. So natural log of x is equal to 9 now. And from here, then I do that as my exponential form. So x is equal to e raised to the 9th power. And when you do that, you still get this same value. Okay, now one nice thing about this one is I don't have to worry about the plus or minus in this case. But when I look at some of these other ones, so we look at these, we're going to go through and kind of do that same kind of process there. So thinking about where x is, I want to kind of undo my order of operations. So I'm going to start by subtracting 7 to both sides here. So that's going to be a -3 log of 10x is equal to a 6. Divide both sides by -3 here. So I have log base 10 of 10x is equal to a -2. This right here is the same as if I rewrite it into exponential form. 10x is going to be 10 raised to the -2 power. And then I can divide both sides by 10. So remember what I'm doing with my exponent rules here. If I'm dividing both sides by 10 to the first, that means this is the same as taking -2 minus 1. So I'm going to subtract my 2 exponents here. So that's 10 to the -3. I don't have to round it off necessarily, but this is the same as, right? 10 to the -3 will be 1, 2, 3. It's 0.0, 1, 2, 3. Wait, am I missing a 0 here? 0.01. Yeah, no, 10 to the -3rd. Yeah. So 1 over, or it's going to be, no, sorry. Yeah, it's 10.001 if I plug that in. My bad. All right. So, and that's just my regular solving process to get through that one. So you can either do this one or this one in this case. So solve log base 5 to x to the 4th equals 20. Now, because I have x to the 4th here, I'm going to suggest that we turn this into exponential form. Because what happens is we're going to do the square root, 4th root property, and we're going to have a plus or minus answer in this case. So because of that, I'm going to rewrite this as x to the 4th is equal to 5 to the 20th power. Okay. Now, one thing I could do is I could multiply out 5 to the 20th power, or I can just take the 4th root of both sides now. When I do that, I'm going to get a plus or minus 5 raised to the, if I take 20 divided by 4, it'd be 5 to the 5th power. So that is the same as plus or minus 3,125. Now, in this case, the -1 does work because if I plug -3,125 in the original problem, raise that to the 4th power, that's fine. That turns into a positive number, and I can evaluate log base 5 of that. So here, the plus or minus does work in this case, because otherwise I would have done this. I would have done 4 times the log base 5 of x equals 20. Divide both sides by 4, so I have log base 5 of x is equal to 5. X is equal to 5 to the 5th power, which is the same as 3,125. Doing it this way, I miss out on that negative number. So that's why it's important to be aware of what's your original problem look like. So if I have an even exponent like that in the problem, then I want to make sure I can account for that positive and negative answer. All right. So one-to-one property. I've skated around this idea. So the one-to-one property of logarithmic functions as well as exponential functions is, well, okay, so it has to deal with this. So if b is greater than 0 and b cannot equal 1, then that means log base b of x is equal to log base b of y if and only if x equals y. Well, that makes sense here. If I have log base 2 of x, log base 2 of 6, the only way this works out is if x and 6 are the same thing. It works the same way with our exponentials. I kind of didn't show this one yet, but if I say 2 to the x is equal to 2 to the 5th, the only way that's possible is if x equals 5. So it's a slightly different setup from what I use where I evaluate log base 2 to both sides, but it's the same concept. We know that the only way for this to be true is if these two are equal to each other. So that's what we're going to look at here for our logarithms. So the way it's written as is, log base 2 of 5 equals log base 2 of 10 minus log base 2 of x minus 4. It's a little bit awkward, but notice how they're all base 2s. So I'm going to condense the right side down and see what I get out of that one to start. So I'm going to have log base 2 of 10 minus log base 2 of x minus 4. That turns into log base 2 of 10 divided by x minus 4. We'll condense it that way. Now, according to a one-to-one property, the only way for this to be true is if 5 equals 10 over x minus 4. And now I can solve this the rest of the way. So I make this multiplied by x minus 4 over 1 and multiply this by x minus 4 over 1. That will cancel that out. I'm going to distribute the 5 over here. So I'll have 5x minus 20 equal to 10. Add the 20 over. So I get 5x equals 30. And then divide by 5. So I get x equals 6. This is a good thing, just like with a lot of our other types of problems of solving. We want to make sure it does work in the original problem. So 6 minus 4 is 2. I can evaluate log base 2 of 2. That one is going to work fine. But we need to be careful with that because sometimes we can create extraneous solutions like taking the logarithm of 0 or a negative number, which will not work. So let's look at the next one. So using, so 3 to the x power is equal to 7. So one way I can set this up for solving is I can evaluate it if I do the log base 3 to the same sides, basically. So what I mean by that is if I have log base 3 of 3 to the x, that's going to equal to the log base 3 of 7. Kind of working backwards with my one-to-one property. Well, the reason I chose log base 3 is because these will cancel out, so that means x is equal to log base 3 of 7. And if I have the calculator that can handle that, I could just do log base 3 of 7. Or I could do my change of base formula. Log base 7 log of 7 divided by log of 3. So that's what I'll do real quick. I'll divide those two out. And I get x to come out to approximately 1.771 for an answer for that one. Okay. So, and that's going to be it for today. So remember, we can use our one-to-one property for both exponential and logarithms. If we have the same base on both sides, or we have the same logarithms on both sides, we can just eliminate the logarithms and exponents, exponential forms and base numbers, and just focus on those other things that are equal to each other. So we're looking at how we solve those using that. All right. That's it for today. Take care, everyone.